Go ahead and pick up a paperclip. Just hold it in your hand for a second. It's almost nothing, right? About 1 gram. Now bend off a tiny piece of it, maybe a tenth of that, a little curled sliver of metal. That sliver weighs next to nothing. Lighter than a butterfly. Lighter than a folded dollar bill. If it fell on your palm, you probably wouldn't even feel it land. And yet, on the morning of August 6th, 1945, somewhere over a city in Japan, a piece of matter weighing about that much, well under a gram, simply vanished from the universe. It didn't burn. It didn't break apart into smoke and ash that you could sweep up later. It ceased to exist as matter at all. And in the same instant, a city died. 80,000 people were gone before they had time to understand what was happening. Buildings a mile out in every direction were flattened into dust. A firestorm raged for hours afterward, swallowing everything that hadn't already been erased. All of that horror came from less mass than the scrap of metal you just bent off your paperclip. So today, here on Feynman's Path, I want to ask the kind of question that sounds almost embarrassingly simple, the kind a child might ask, but which happens to be one of the deepest questions in all of physics. What does it actually mean for matter to disappear? When I was in school, I learned a law that seemed as solid as the ground under my feet. Matter is conserved. It can't be created. It can't be destroyed. You can melt it, burn it, smash it into smaller pieces, but add up everything at the end of the day, and the total amount of stuff in the universe never changes. This was the law of conservation of mass, and for over 100 years after the chemist Antoine Lavoisier nailed it down in the 1780s, it was treated as gospel. Every branch of chemistry and engineering was built on top of it. Weigh your ingredients before a reaction, weigh the products after, and the numbers matched. Clean, satisfying, complete. Except there was a tiny crack in the foundation. The law wasn't quite the absolute truth everyone believed it was. In 1905, a young man working in a patent office in Bern, Switzerland, had a quiet but dangerous idea. Albert Einstein published a short paper with an almost shy little title, something like, "Does the inertia of a body depend upon its energy content?" Hardly anyone noticed it at the time. 3 pages, no fanfare. But buried inside those 3 pages was arguably the most explosive equation ever written down by a human being. The idea was this. What if mass and energy aren't 2 separate things at all? What if they're the exact same thing, just wearing different costumes? You've all seen the equation. It's on t-shirts, it's on coffee mugs. People who have never taken a physics class in their life can recite it. E equals mc squared. But today I don't just want you to recognize that equation. I want you to actually feel what it's telling you, because the truth inside those 5 symbols is frankly terrifying. Let's take it apart slowly. E is energy, measured in joules. M is mass, measured in kilograms. And C is the speed of light. 3 clean letters. But almost all the drama in this equation comes from just one of them, squared. The speed of light isn't just a big number. It's an almost incomprehensibly enormous one. Light travels about 186,000 miles every single second. In the time it takes you to snap your fingers, a beam of light could circle the Earth more than 7 times. It could go from New York to Los Angeles and most of the way back before you finished reading this sentence. Nothing you've ever experienced in your daily life comes anywhere close to that speed. And we don't just use C, we square it. We multiply that already monstrous number by itself. In metric units, the speed of light is about 300 million meters per second. Square that, and you get 9, followed by 16 zeros, 90 quadrillion. A number so large, your brain has no everyday reference point for it. Nothing in your lived experience prepares you to grasp 16 zeros. That monstrous number is the exchange rate between mass and energy. Think of it like a currency exchange booth at the airport. You hand over a small amount of one currency and the rate tells you how much of the other you get back. Between mass and energy, the exchange rate happens to be the speed of light, squared. Which means even a microscopic, almost laughably small amount of mass, once converted, hands you back a staggering, sanity-bending quantity of energy. Let me make this concrete. Picture 1 kilogram of anything. A bag of sugar, a few apples, a fist-sized rock. If you could convert that entire kilogram completely and perfectly into pure energy, you'd unleash about 90 quadrillion joules. To put that into perspective, the entire United States uses something like 100 billion kilowatt hours of electricity in a month. Fully converting 1 kilogram of mass would release around 25 billion kilowatt hours. A bag of sugar, turned entirely into energy, could power a small country for an entire year. Of course, nobody can actually do this. You can't rip open a sugar packet and convert it all into pure energy. If we could, we wouldn't need coal plants or nuclear reactors or oil at all. 1 bag of sugar a year could run a city, but nature does not hand over energy that easily. That conversion process sits locked behind an enormously thick steel door, and for nearly all of human history that door stayed shut. Let me show you just how feeble our everyday energy-releasing processes really are compared to that door. Burn a log of wood and you get heat and light. According to Einstein, technically, some tiny sliver of mass did convert into energy. And strictly speaking, that's true. But the amount converted is so absurdly small that no scale humans have ever built could measure it. Burn a kilogram of wood, and the combined weight of the ash, the carbon dioxide, the water vapor, everything that comes out, is very slightly lighter than the wood and oxygen that went in. But the difference is something like 1 part in 10 billion grams. Completely unmeasurable. Which is exactly why, for all practical purposes, the law of conservation of mass works perfectly well in chemistry. Lavoisier wasn't wrong. He was just operating right at the edge of what his scales could detect. Chemical energy comes from electrons shuffling around. That's the entire story of chemistry, really. Atoms sharing and trading electrons, forming new bonds, breaking old ones. Burn hydrogen and oxygen together, and the electrons settle into a more comfortable arrangement, releasing a bit of energy as they go. Detonate a powerful chemical explosive like TNT, and nitrogen and oxygen atoms are violently rearranging their bonds, dumping that energy out as a shockwave. But the amount of energy involved in shuffling electrons is laughably tiny compared to the mass of the atom itself. Even something as destructive as a TNT explosion converts only about 1 part in a billion of its mass into energy. 1 in a billion. Practically nothing changed at all. Here's a way to picture the scale. Imagine the total mass energy of 1 atom as a 100-story skyscraper. The chemical energy you get from rearranging electrons is like scratching off a single flake of paint from the lobby wall with your fingernail. But nuclear energy is something else entirely. Not slightly different, roughly 1,000,000 times different. Nuclear energy isn't scratching paint in the lobby. It's detonating one of the central load-bearing pillars holding up the whole tower. It reaches straight into the deepest core of the atom, the nucleus, and rearranges the protons and neutrons themselves. And what comes pouring out of that is energy on a scale that defies intuition. That's why a reactor the size of a single room can replace a power plant the size of an entire city block. That's why a nuclear submarine can carry fuel lighter than a car and patrol the ocean for 25 years straight. Nuclear fuel isn't just somewhat denser in energy than chemical fuel. It's millions of times denser. And the whole difference comes down to this. Chemical reactions only touch the outer electrons. Nuclear reactions touch the nucleus, the place where essentially all the mass of the atom actually lives. To understand why, I need to take you down inside the atom, into the nucleus, into the place where the real energy is hiding. You probably have a rough picture of an atom in your head. A dense little nucleus of protons and neutrons at the center, with electrons buzzing around it at a distance. Compared to the whole atom, the nucleus is unbelievably small. If you blew an atom up to the size of a football stadium, the nucleus would be a single marble sitting at the center of the field. And here's the strange part. That tiny marble contains nearly all the mass of the entire atom. Something like 99.9% of it. The electrons buzzing around weigh almost nothing, and the space between the nucleus and the electrons is, for all practical purposes, empty. So the nucleus is tiny, unbelievably dense, and absolutely packed with particles. The protons inside it all carry positive charge, which means they are violently repelling each other. Imagine holding dozens of powerful magnets, all facing the same pole outward, and trying to force them together by hand. They would fight you, every single one of them trying to fly apart. Electromagnetic repulsion wants to tear the protons in a nucleus to pieces, and yet, somehow, they stay locked tightly together. What's holding them is something called the strong nuclear force, the most powerful force known in all of nature. If electromagnetic repulsion is a determined arm wrestler, the strong force is a hydraulic press capable of crushing tons of steel. Inside the tiny confines of the nucleus, the strong force completely overwhelms the electrical repulsion trying to blow it apart. But here is the crucial part. That binding together is never free. The tremendous energy required to hold the nucleus together has to come from somewhere, and it comes from mass. If you weigh a nucleus very precisely, it turns out to be a tiny bit lighter than the sum of its individual parts weighed separately. This is the heart of everything, so let me walk through it carefully. Take a helium nucleus, 2 protons and 2 neutrons. Weigh a free proton by itself, weigh a free neutron by itself. Add up 2 of each like simple arithmetic. Now weigh the helium nucleus once it's all bound together. Remarkably, the bound nucleus weighs less, noticeably less, by about 0.7% of the total mass. Where did that missing mass go? It transformed into the binding energy holding those 4 particles together. This isn't a metaphor or some loose figure of speech. The nucleus is literally lighter than its own contents. Mass genuinely vanished, converted into the binding energy that holds the particles in place. Take that missing mass, multiply it by the speed of light squared, and you get exactly, precisely, the binding energy, with no error at all. Einstein's equation proven with breathtaking precision at the nuclear scale, which means every nucleus inside your body right now, in this desk, in the air you're breathing, is just a little bit lighter than the sum of its individual particles. That missing sliver of mass is the price, the toll paid, for existing as stable, organized matter rather than a scattered cloud of loose particles. So that's the first key idea. Mass binds the nucleus together, and that binding shows up as a tiny loss of mass. Now let's add one more layer, because this is the pattern that makes the atomic bomb possible at all. Not every nucleus in the universe is bound equally tightly. Some hold together far more snugly than others. If you graph the binding energy per particle against the size of the nucleus, you get a striking curve, shaped almost like a mountain. Light elements like hydrogen, helium, lithium climb steeply up that mountain. Add more particles and each one binds more tightly. The curve flattens out and finally peaks at iron, element number 26, with 56 particles in its nucleus. Iron sits right at the summit. Its nucleus is the most tightly bound, most stable, most energetically satisfied nucleus in all of nature. Past iron, heading toward heavier elements like gold or uranium, the curve slopes back downward. Heavy nuclei are actually less tightly bound than iron. They're so bloated and crowded that the short-range strong force can't quite reach all the way to the particles sitting out at the edges, while the electrical repulsion between all those protons keeps getting worse and worse as the nucleus grows. This mountain-shaped curve is one of the most important graphs in the history of physics, because it explains both fusion and fission in one picture. Fusion takes light elements on the left side of the curve and smashes them together, climbing toward the peak at iron. Fission takes heavy elements on the right side, like uranium or plutonium, and splits them apart, also climbing toward that same peak. Both processes are moving toward iron. Both release a burst of energy equal to the difference in binding energy. Both are converting a sliver of mass into a flood of energy. Iron sits at the summit. It's the dead end of nuclear energy. You cannot extract energy from it by fission or by fusion. Once you reach iron, the game is over, and the terrifying energy locked inside a bomb comes from exactly this mountain. If you forcibly split a heavy nucleus like uranium, way out on the right side of the curve, into 2 medium-sized fragments, those fragments land closer to the peak. They're more tightly bound per particle than the original uranium was. The difference in binding energy has to go somewhere, and it goes out as kinetic energy, as heat, as deadly radiation. That's the violent energy of fission. And because binding energy is, in the end, just mass, the combined weight of the 2 fragments is very slightly lighter than the original uranium nucleus, about 0.1% lighter. Mass has vanished from the universe, a tiny fraction, sure. But multiply that tiny mass loss by the speed of light squared, that monstrous 16-0 exchange rate, and every single splitting atom unleashes a horrifying amount of energy. A single uranium-235 atom releases roughly 200 million electron volts when it splits. A single TNT molecule burning releases about 3 electron volts. That's a difference of 60 to 70 million times. Not double, not 100 times. Tens of millions of times more energy from one atom splitting than from one chemical reaction. That unbridgeable gap is exactly why a few hundred grams of converted mass can level a city while tons of conventional explosive barely dent a single building. Now let's walk through how engineers actually weaponize this. Uranium comes in different flavors, called isotopes. The common one, uranium-238, makes up over 99% of natural uranium. It's stubborn. Hit it with a neutron and it just absorbs it, sitting there inert, refusing to split. The rare isotope, uranium-235, makes up less than 1% of natural uranium, maybe 7 atoms out of every 1,000. But this isotope is wildly unstable. Hit it with even a slow, lazy neutron and it tears itself apart almost instantly. When a uranium-235 nucleus splits, it breaks into 2 smaller daughter nuclei, but never the same pair twice. It's wildly unpredictable, splitting into barium and krypton one time, strontium and xenon another, cesium and rubidium another. Dozens of possible combinations, nature rolling dice with every single split. But whatever the combination, one thing always happens. Both fragments go flying apart at roughly 3% of the speed of light, something like 20 million miles an hour. They smash violently into surrounding atoms, transferring that ferocious energy and heating the material almost instantly. That's where the unbearable heat of the explosion actually comes from. Not chemical burning, but shattered nuclear fragments hammering into everything around them at relativistic speed. And as the nucleus splits, it also spits out 2 or 3 free neutrons, racing off at thousands of miles per second. Each of those neutrons is a messenger of the next round. If one of them happens to strike another uranium-235 atom, that atom splits too, releasing more energy and more neutrons. 1 becomes 2, 2 becomes 4, 4 becomes 8, 8 becomes 16. This is exponential growth, and human intuition is catastrophically bad at predicting how fast exponential growth can spiral. Starting from a single fission, after 10 generations you have roughly 1,000 splits. After 20 generations, 1,000,000. After 30, 1,000,000,000. After 40, 1,000,000,000,000. After about 80 generations, more fissions are happening than there are atoms in the entire solar system. And each generation takes only about 10 nanoseconds, 100 millionth of a second. The entire 80-generation cascade completes in roughly a microsecond, faster than sound can travel across a room, faster than any alarm, any reflex, any warning system could possibly respond. That's why there's no siren before the flash. The physics simply outraces human perception entirely. But triggering this chain reaction inside an actual device is brutally difficult because neutrons fly off in every direction, and most of the uranium dug out of the ground is the stubborn, non-fissile uranium-238, which just swallows neutrons without splitting. So bomb designers need to pack in a high concentration of uranium-235, dense enough and large enough that neutrons hit their targets before they either escape or get absorbed uselessly. This is where the idea of critical mass comes in. It's the minimum amount of fissile material needed for the chain reaction to sustain itself rather than fizzle out. Below critical mass, the reaction starves itself, losing more neutrons to escape and absorption than it creates. Above critical mass, the reaction runs away, growing uncontrollably. But here's the brutal contradiction at the heart of every fission weapon. The chain reaction is racing to pile up more and more energy every 10 nanoseconds. But that same energy, the instant it's released, blasts the material itself outward, expanding it, tearing the pieces apart. The moment the density drops below critical mass, the runaway reaction instantly chokes and dies. A bomb is, in a very real sense, racing against its own self-destruction. This is exactly why the bomb dropped on Hiroshima, known as Little Boy, was so brutally inefficient. The chain reaction only had a tiny sliver of time to burn through the uranium before the explosion blew the whole device apart. Of the 64 kilograms of highly enriched uranium packed inside it, less than 2% actually underwent fission before the device tore itself to pieces and the reaction sputtered out. The rest, 98% of that achingly expensive material, was simply scattered uselessly across the Pacific sky. Building that bomb in the first place required separating uranium-235 from its stubborn sibling, which is chemically a nightmare, because the two isotopes behave almost identically in every chemical reaction. The only difference is that 238 carries 3 extra neutrons, making it barely 1% heavier. Separating them is like dumping 2 piles of sand onto a football field, with grains differing in weight by just 1%, and trying to sort them with tweezers. The Manhattan Project actually pulled off that impossible task. They built an entire secret city at Oak Ridge, Tennessee, employing roughly 75,000 workers behind barbed wire and armed guards, most of whom had no idea what they were actually building. Vast gaseous diffusion plants ran around the clock, forcing corrosive uranium hexafluoride gas through barriers pierced with holes a millionth of an inch wide, relying on the fact that the lighter isotope passes through marginally, almost imperceptibly, faster. The enrichment gained with each pass was razor-thin, so the process had to be repeated thousands upon thousands of times, like distilling the finest vodka over and over again. Alongside that, massive electromagnetic separators called calutrons hummed away, bending streams of charged uranium ions through powerful magnetic fields, the lighter isotope curving along a slightly tighter arc and landing in a separate collector mere fractions of an inch away. The whole operation consumed almost 3 years, billions of dollars, and the labor of tens of thousands of people. And the final yield of all that effort was about 64 kilograms of highly enriched uranium, of which, in the end, only about 7/10 of a gram actually converted into energy. 3 years, an entire secret industrial city, to steal away less mass than a paperclip. The bomb built from that uranium, little boy, was crude by later standards, a simple gun-type design. A hollow cylindrical target of uranium sat at one end of a long steel barrel, and a smaller uranium projectile sat at the other. Conventional explosive charges fired the projectile down the barrel into the target, smashing the two pieces together to exceed critical mass and ignite the chain reaction. Simple in concept, but the engineering timing had to be razor precise, because the two masses had to slam together fast enough that the chain reaction could build to a catastrophic level before the heat of the initial fissions blew the device apart. A microsecond of sloppy timing and you'd get a fizzle instead of a detonation. At 8:15 in the morning on August 6, 1945, a B-29 bomber named the Enola Gay released Little Boy from roughly 31,000 feet above Hiroshima. The bomb fell freely for about 44 seconds. At the predetermined altitude, a barometric trigger fired the explosive charge. The uranium projectile screamed down the barrel and slammed into the target. In less than a millionth of a second, the chain reaction grew from nothing into a force capable of erasing a city. And here's the number that should genuinely take your breath away. Of those 64 kilograms of agonizingly enriched uranium, only about a kilogram actually underwent fission. Less than 2% of the fuel was even used. And of that 1 kilogram that did split, only about 1/10% of its mass actually converted into energy. Which means the total mass that vanished from the universe, that crossed the exchange counter of c² and turned into pure energy, was approximately 7/10 of a gram. Less than the weight of that paperclip you bent earlier. That 7/10 of a gram is not the weight of the bomb's steel casing. It's not the weight of all the uranium loaded into it. It's not even the weight of the 1 kilogram that fissioned. It is, literally, the amount of mass that ceased to exist, converted at that merciless exchange rate into energy equivalent to roughly 15,000 tons of TNT. To put that scale into perspective, imagine a freight train loaded with 15,000 tons of TNT, a train so long it would take you a full hour to walk from the locomotive to the caboose. All of that destructive power came from a piece of matter lighter than a paperclip simply vanishing. Let's walk through exactly how that energy tore the city apart. Because once unleashed, it didn't arrive as a single bang. It split into 3 distinct forms of devastation, each destroying the city in a different way. And the unfolding of it is, in its own terrible way, a lesson in physics. About 35% of the energy came out as thermal radiation, heat and light. The fireball's surface reached temperatures comparable to the surface of the sun, scorching the ground below for a few seconds. Within roughly a mile of the blast, people were burned by radiant heat so intense it ignited their clothing and seared flesh instantly. Shadows of people who had been standing in the open were permanently burned into concrete walls and pavement, the only trace left behind of someone who existed in that spot the instant the flash went off. This thermal pulse traveled at the speed of light, so there was no siren, no warning, no time to flinch. The blinding flash and the burning heat arrived in the exact same instant. About 50% of the energy came out as blast wave, a wall of crushing overpressure. Pump that much energy into the air that quickly, and ordinary air itself becomes a weapon. It compresses into a shockwave that expands outward faster than the speed of sound, initially traveling at roughly 1,000 miles an hour before gradually slowing. Behind that shockwave, air pressure spikes to several times normal atmospheric pressure. The human body can survive a great deal, but a pressure differential of 3 or 4 times normal pressure between the front and back of your body is enough to rupture organs and shatter bone. Concrete walls crumbled into powder. Steel roofing bent like tinfoil. Windows didn't just shatter, they exploded inward like shotgun blasts, every shard becoming a lethal projectile. And after the outward blast wave passed, a strange and terrible reversal happened. A partial vacuum formed behind the shockwave, and air came rushing back inward toward the center of the explosion, toppling structures that had barely survived the outward blast in the opposite direction and dragging fresh oxygen in from every side to fuel the firestorm that followed. Within roughly a mile, nearly every building was flattened, not just cracked, but ground down to rubble in less than a second. A bustling city turned into a lunar landscape in the blink of an eye, and the remaining 15% of the energy came out as nuclear radiation, the quietest and most insidious killer of all. Gamma rays and neutrons, invisible, odorless, passed silently through rubble and through human bodies alike. Gamma rays are fundamentally the same kind of particle as visible light, just carrying roughly 100,000 times more energy per photon. At that energy level, they don't bounce off a wall the way a flashlight beam does. They pass straight through flesh and bone, tearing electrons away from atoms inside living cells and severing the delicate chemical bonds that hold DNA together. Neutrons cause damage differently, but just as lethally, slamming into atomic nuclei like billiard balls and knocking atoms violently out of their molecular positions, like hurling a bowling ball through a shelf of fine china. This radiation also traveled at the speed of light, arriving in the same instant as the blinding flash, before any sound, before any blast wave reached you. People sheltered behind thick concrete or underground might have survived the heat and the shock wave, only to have the radiation pass through anyway. Weakened but never fully stopped, beginning a slow and silent countdown inside their bodies. Some developed acute radiation sickness and died within hours or days, their bone marrow destroyed beyond the point of producing new blood cells. Others appeared completely unharmed at first, walking out to help neighbors and search for family, only to have their hair fall out in clumps days or weeks later, their skin marked by purple bruises, their gums bleeding. The radiation had targeted the fastest dividing cells in the body first, which are tragically the very cells the body needs most to heal itself. A flash that tore the sky open, a shockwave that erased a city, radiation that burrowed into the marrow of survivors. A firestorm born from rubble and rushing wind. All of it from less than a gram of mass that briefly lost its way and vanished from existence. Now here's where I want you to pause, because most people, overwhelmed by the horror, stop thinking right at this point. Don't stop here. Remember, I told you earlier that little boy was clumsy and shockingly inefficient. Less than 2% of the uranium even fissioned, and of that, only a sliver of mass converted into energy. The overall conversion efficiency of the entire device was pitifully, almost embarrassingly small. And even at that abysmal efficiency, it was enough to erase 80,000 lives and wipe a city off the map. So what if, hypothetically, you could push that efficiency all the way to its absolute limit? Nature actually has a process that converts mass to energy with 100% perfect efficiency. We call it matter antimatter annihilation. When a particle meets its mirror image antiparticle, an electron meeting a positron or a proton meeting an antiproton, they don't just react, they completely annihilate each other. Every last scrap of mass converts into pure energy, nothing left over. No residue, no waste, just photons, pure light and energy. If you could somehow gather 1 kilogram of matter and 1 kilogram of antimatter and let them collide, the resulting explosion would be equivalent to roughly 43 megatons of TNT, about 1,000 times more powerful than the bomb that destroyed Hiroshima, and that's from just 2 kilograms of material combined. We obviously don't have the technology to build an antimatter bomb today. Our most advanced particle accelerators can only produce a handful of antimatter atoms at a time, at staggering cost. If you wanted to collect a single gram of antimatter, the price tag would run into the tens of trillions of dollars, easily the most expensive substance in the known universe. But here's what should send a chill down your spine. Our physics has no objection to it. The beautiful equation doesn't care how you go about converting mass into energy. It simply, coldly, indifferently tells you the exchange rate, and that exchange rate is always equally merciless. And the equation runs just as perfectly in the opposite direction, in the direction of creation rather than destruction. The very same equation, the very same 5 symbols that incinerated Hiroshima and took tens of thousands of lives, also perfectly explains why the sun blazes in the sky every single day. Not fission splitting heavy atoms apart, but fusion crushing light atoms together under unimaginable pressure. Hydrogen fusing into helium, and the sliver of mass that goes missing in the process becoming sunlight. Right now, in this very moment, as you listen to this, Deep in the sun's core, something like 600 million tons of hydrogen are being fused into about 596 million tons of helium every single second. That means roughly 4 million tons of mass simply vanish from the universe every second, just gone. And through that exact same c-squared exchange rate, it becomes the warm sunlight touching your skin right now. 4 million tons of mass lost every second sounds catastrophic, but the sun is so unimaginably massive that this kind of weight loss is barely a rounding error. It's been burning at this insane rate for about 4.5 billion years, and it has enough fuel left in its tank to keep burning for roughly another 5 billion years. The equation that flattened Hiroshima and the equation that lights up the night sky with stars are not different equations. They're the exact same arithmetic, the exact same physics. The only difference is environment and scale. Whether 10 million degree fire burns inside a perfectly controlled gravitational furnace 93 million miles away, or whether an uncontrolled chain reaction detonates 2,000 feet above a sleeping city. That's the only difference. An accident of arrangement. Now let me step back for a moment and confess something. The realization that I personally find the most unsettling out of this entire story. The one that kept me up at night when I first truly understood it. That devastating energy that erased Hiroshima wasn't suddenly conjured into existence by human hands. It was always there. It had been sleeping quietly inside the nucleus of those uranium atoms for an unimaginably long time. Those uranium atoms were forged billions of years ago, in the violent death throes of some massive star, in a supernova explosion, itself powered by ferocious nuclear reactions. The heavy atoms born in that searing cataclysm drifted through cold, empty interstellar space for billions of years before becoming part of the swirling cloud of gas and dust that eventually formed our solar system. They settled into the cooling crust of the young Earth and lay dormant in dark rock for 4.5 billion years. Then human miners dug them out of the ground, refined them in chemical plants, enriched them in a secret city in Tennessee, machined them into precise metal components, assembled them into a weapon, and flew them over a city. Through that entire unimaginable journey, from the heart of a dying star to the sky above Hiroshima, that terrifying binding energy sat locked inside the nucleus, waiting. We didn't create that energy. Energy cannot be created or destroyed. That is one of the most absolute and unyielding laws in all of physics. All we did was find one particular keyhole in a lock the universe had already sealed and figure out how to force it open. We learned to cruelly rearrange the particles inside the nucleus. And as a result, a tiny fragment of mass no longer needed to hold the family together. That liberated mass passed through the exchange counter and turned into a blinding flash and a wall of fire that swept across a city. This universe has been sitting precariously on top of this kind of terrifying arsenal since the very beginning. Every pebble you kick down the street, every glass of water you drink, every handful of sand on a beach carries inside its atoms an amount of energy your brain simply cannot intuitively grasp. We walk across that bomb every single day. We drink it. We breathe it. We are even made out of it. Your body is built from roughly 7 times 10 to the 27th atoms. If you could flip some magic switch and release every bit of nuclear binding energy locked inside those atoms, you would unleash energy equivalent to thousands of hydrogen bombs detonating at once. Each one of you listening to me right now is, in a very real sense, a sleeping arsenal of unimaginable destructive potential walking around in human form. But you are completely safe. Because the strong nuclear force, the universe's silent security guard, holds those nuclei together with such ferocious grip that no ordinary everyday process can ever pry them apart. Chemical reactions can't even scratch the surface. You could burn it for 100 years and it wouldn't budge. You could strike it with the heaviest hammer imaginable and nothing would happen. Breaking that bond requires either an extremely precise, carefully engineered nuclear reaction or particle accelerators powerful enough to forcibly tear it apart. The energy is genuinely pulsing beneath your skin, but for all practical purposes, it sits welded shut behind an iron door. With one single, accidental exception, the door the universe happened to leave just slightly ajar. Uranium-235. The only naturally occurring substance where a single, lazy, crawling neutron is all it takes to kick that door wide open. The reason this particular detail moves me so deeply runs a bit deeper than just the destruction itself. The speed of light isn't some arbitrary figure that scientists voted on in a committee meeting. It's a fundamental property of the universe itself, baked permanently into the very geometry of space-time, not something we get to negotiate or adjust for our convenience. Because the exchange rate between mass and energy happens to be the speed of light squared, exactly how much hellfire is packed inside a single gram of matter isn't determined by human ingenuity or clever engineering. It's set, coldly and absolutely, by one of nature's fixed constants. Imagine for a moment that you were some kind of creator, designing a brand new universe from a blank slate. You could, in principle, set the value of C to be anything you wanted. If you built a universe where light moved more slowly than it does in ours, the exchange rate between mass and energy would plummet. The same kilogram of mass would yield a far more modest amount of energy. Human-made nuclear weapons would be barely more powerful than a large pile of dynamite. The stars overhead would burn dimmer, flickering weakly, or perhaps never igniting at all. Stellar fusion that forges carbon and oxygen deep inside stars depends entirely on the energy scale that C sets. Life as we know it might never have had the chance to exist in such a sluggish universe. Now imagine the opposite, a universe where light moved unimaginably faster than it does here. A single gram of matter would carry a far more vast and uncontrollable reservoir of energy. A single human-made bomb could be powerful enough to crack a planet in half. Stars would burn with blinding, savage intensity and burn themselves out almost instantly. Our universe, with that particular precise value of roughly 186,000 miles per second, runs on a strange and delicately balanced kind of mathematics. It's exactly the value that grants us the warm, gentle starlight in the night sky, and at the same time hands humanity the means to reduce entire civilizations to ash with the press of a button. The same furnace that warms us against the cold of space and the same weapon capable of ending everything exist under the very same equation, the very same constant of nature, the very same cruel and beautiful arithmetic. So let's bring this long journey to a close. The next time a paperclip rolls across your desk, don't just toss it aside. Pick it up, hold it for a moment, and really feel the weight of that small piece of metal. Remember the 7/10 of a gram that vanished from existence above Hiroshima more than 70 years ago. And consider that the bent-off sliver still sitting between your fingers, if it ever passed through that same exchange rate of E equals mc squared, could in principle release an explosion equivalent to roughly 20,000 tons of TNT. A bigger blast than the entire bomb that ended a city, sleeping quietly inside the unremarkable little scrap of metal in your hand right now. The only thing standing between you and that catastrophic energy is the magnificent stubbornness of the strong nuclear force, and the simple fact that no human being has yet figured out how to pick that particular lock. We've only managed to force open one loose latch on one particular isotope, uranium-235. This is the true meaning of E equals mc squared. It isn't a dry abstraction scrawled on a chalkboard. It isn't a catchy slogan from a science magazine cover. It is such an unflinchingly accurate description of the pulsing reality all around you that the entire history of science struggles to produce anything quite so unsettling. 5 symbols. 3 letters, 1 number, 1 equals sign. And those small symbols are quietly whispering in your ear, telling you that everything you see, everything you touch, the people you love, every grain of sand on every beach, is a silent reservoir of terrifying power, patiently waiting for someone or something to eventually find the key. I think back often to my younger years working out in the desert at Los Alamos on this very project. Back then, all of us scientists were utterly consumed by the immediate technical puzzle in front of us. Could we actually make this device work? Could we sustain a chain reaction without it sputtering out? Could we calculate the critical mass precisely enough? How large would the resulting blast actually be? My team and I spent night after night hunched over chalkboards calculating yield, trying to predict exactly how much energy would actually be released when it detonated. It was, in a strange and terrible way, an elegant mathematical puzzle. And we were all so deeply absorbed in solving that puzzle that we momentarily lost sight of what our answer actually meant for real human beings in the real world. Then, at 5:30 in the morning on July 16th, 1945, in a desolate stretch of New Mexico desert near a place called Alamogordo, humanity detonated its first nuclear explosion, the Trinity test. It used plutonium rather than uranium, with a completely different and far more intricate implosion design, but the underlying physics was identical, E equals mc squared. Mass, shedding its disguise and becoming pure, naked energy. I was stationed roughly 20 miles from ground zero. They handed out dark welding glass for everyone to look through. When the countdown reached 0, The loudspeakers told everyone to lie face down with their eyes shielded behind that dark glass. But thinking it through scientifically, that instruction struck me as a bit excessive. The real danger to the eyes from that flash would be ultraviolet light, and the ordinary windshield glass of the truck I had ridden in already blocked ultraviolet light completely. So I climbed into the driver's seat of that truck, skipped the dark goggles entirely, and watched the whole thing unfold through the windshield with my own bare eyes. As far as I know, I might be the only person who watched humanity's first nuclear detonation completely unfiltered, from start to finish. The first thing that arrived was the light. A flash brighter than anything I had ever witnessed in my life, bright enough to wash out every color I had ever known. I genuinely had not imagined that light of that intensity could exist in this world. The dark desert floor, the silhouette of distant mountains, everything was thrown into sharp, X-ray relief, as though someone had flipped a switch and placed a second sun on the desert floor for a fraction of a second. Then came the fireball, swirling violently, orange and red and blinding white gas climbing into the sky as though it intended to swallow the heavens whole. And only much later did the shockwave reach us, taking nearly a minute and a half to cross the 15 or so miles between us and the blast. A sharp, hot slap of pressure rushed past, followed by a deep, rolling thunder that echoed off the distant mountains again and again, like the roar of some enormous beast. The scientists around me erupted in cheers. Some of them jumped and even danced with joy. There was a powerful sense of relief in the air, as though an enormous weight had finally lifted off our shoulders. We did it. The theory held. The math on the chalkboard hadn't been wrong. The yield matched what we calculated almost exactly. The size of that fireball and the reports coming back from the field confirmed that our predictions had been chillingly accurate. But once the cheering died down, hours later, I distinctly remember a cold, strange feeling creeping into a corner of my mind. Like waking from a vivid and disturbing nightmare, wiping the sweat from your brow, only to look around and realize this wasn't a dream at all, but irreversible reality. And exactly 3 weeks later, Hiroshima was gone. A few days after that, Nagasaki followed. After everything ended and the war finally stopped, I remember sitting in an ordinary diner in New York City. I watched people walking by on the sidewalk outside, completely unaware, completely ordinary. I looked up at the steel skeletons of new buildings going up nearby. And a terrible thought struck me like a hammer. Why are these people bothering to build anything at all? Don't they understand that all of this beautiful civilization could be wiped out in a single blinding flash? What's the point of constructing some magnificent bridge that might evaporate into nothing within a few days? It took a long time, and a great deal of grief, to shake off that crushing sense of futility. What I eventually came to understand is this. The only rational response for someone who truly grasps the terrifying power locked inside matter is not to cower in fear of annihilation, but to keep building anyway, and to keep asking questions about the nature of the universe regardless. Because whether we choose to study this equation or turn away from it in fear, the cold, indifferent laws of physics remain exactly the same either way. The exchange rate between mass and energy is not something humanity invented. We merely stumbled upon something that was already there, waiting. E equals mc squared doesn't care about human fear, human grief, or any nation's political strategy. It is simply a cold, objective truth about how this universe happens to be built. It was true long before we discovered it, and it will remain true long after humanity has vanished and been forgotten. 0.7 of a gram. What I've shared with you today on Feynman's path isn't simply a frightening piece of history about a single bomb dropped decades ago. It's a story about the deepest blueprint underlying the entire structure of the universe we live in. What matter truly is, what energy truly is, and the profound, spine-chilling truth that the two are, in the end, simply two faces of the exact same coin. Your body, right now, is built from the very same kind of matter that holds the very same kind of energy that once tore Hiroshima apart. Inside you, quietly, sits enough nuclear potential to either light up countless new civilizations or to end them entirely. The same atoms, the same forces, the same equation. The only thing that differs is arrangement and the choices we, in our limited wisdom, decide to make. Sit with that heavy truth for a moment. Let it make you a little uncomfortable, even a little afraid, because the universe owes us no obligation to be comforting. It doesn't simplify or soften its own laws just so that fragile creatures like us can sleep peacefully at night. The only thing the universe truly owes us is brutal honesty. And that honest truth is that 5 small symbols, scrawled in chalk, 3 letters, 1 number, and an equal sign, describe a world far more dangerous, far more dazzling, and far more awe-inspiring than our limited, everyday senses could ever suggest on their own. More than 70 years ago, above Hiroshima, a mere 7/10 of a gram of mass briefly stirred awake. And the rest of the unimaginable mass still spread throughout this universe remains quietly, patiently asleep. If you ever wanted to write me a letter, not about bombs or reactors or the mechanics of any of this, but about what you personally believe is the most important philosophical consequence of E=mc² for the nature of reality itself, I would genuinely love to read just 1 line of your thoughts on that. That's everything I have for you today here on Feynman's Path. Thank you, truly, from the bottom of my heart for staying with me all the way through this one. If this video managed to spark some new flame of curiosity in your mind, please consider subscribing to the channel and turning on notifications. I'll see you again soon with another fascinating story.